Hello everyone, we're going to go ahead and start with our fourth and final video of this unit, and we're actually going to look at how to determine the rate of effusion between two gases. Now, effusion, diffusion sound very close to each other. Diffusion we've heard of before. Now, diffusion is just a mixing of gases. Usually what we mean is, if I was to stand at the front of a room and spray X, there will be a certain amount of time that it would take for me to spray it to the point where it reaches the furthest part of the room. Now, effusion is going to be a very similar concept, except instead of being in open space like we've looked at for diffusion, it's going to be escaping through a tiny, tiny, small part of the chamber. So, in my mind, I think of it as, here we go, good example. When you buy balloons or someone buys you balloons, they fill them with helium. After a few days, you notice that they begin to drop, to sag a little bit. They're still flying, they're still up there, but they're not going as high, the balloon's not as full. One of the reasons is because of what we call effusion. The gas particles are actually able to go through the small little parts or spaces between the molecules of the acrylic or whatever material the balloon is actually made of. Now, the rate of effusion is the speed at which the gas is actually leaving that container. Example of what we have here. Notice we have high concentration of gas here. We have our pinhole, and this part is a vacuum because it's lower. It has a lower amount of gas, lower pressure, and so forth. So the rate at which it leaves is going to be directly proportional to the size of the molecules that we're dealing with. This is the basic formula that we're going to use. Rate of effusion for gas 1 is equal to rate of effusion for gas, over the rate of effusion for gas 2, which is going to be equal to the square root of each of these terms. That is the molar mass of these gases. Now, to look at an example, we have in your packet, we have, sorry, lost my page. Here we go. If we're looking at the Graham's Law worksheet, this is where we're going to see our first example of this. Number 5 says calculate the ratio of the rate of effusion of methane versus silicon tetrahydride. So if we're taking a look at both of these compounds, it says we're going to do square root of M2 over M1. How do you determine which one is M2 and which one is M1? Well, the one that has the larger mass, because we usually want something that's going to be over 1, the one that has the larger mass is the one that's going to go on top. So if I have, I'll write it here on the bottom, silicon tetrahydride versus methane, which is CH4. Methane has a mass 12.01 plus 4.04, that'll give us 16.05. And for silicon tetrahydride, we still have the 4.04, but then we have 28.09. That's going to give us approximately 32.13. So when we set up our rate of effusion, it's going to be 32.13 square root divided by 16.05 square root. This is going to help me to be able to get the rate of effusion, or the comparative rate of effusion between the two. So when I take this and divide it, I'm actually going to end up with approximately 1.41. So the methane is going to effuse or leave 1.41 times faster than would be the gas for the silicon tetrahydride. Now, we can use that information to actually make some other predictions and to see how things will work later on down the line in terms of our interactions between our gases. But that's actually where we're going to wrap this part of the video up at. Now, the last thing that we need to cover, and this is what ties all of this together, hopefully you'll be able to see it, is the difference between what we call real and ideal gases. All of these discussions that we've had up until this point have been dealing with what we call ideal gases. And basically it's something that doesn't actually exist, as you're seeing here on the screen. But there are certain situations at which we can put these or make these conditions more favorable. What do I mean? We know that all gases have different sizes. Because they have different masses, different densities, and so forth, that would make things very difficult for us to be able to actually calculate. So what we do instead is we put them at high pressure and the temperature low. Sorry, this would actually be non-ideal. If we have high pressure, low temperatures, the molecules or the particles are more likely to stick together because they're going to interact under um, intermolecular forces. Now, if we wanted to get out of this situation, we'd have to have very low pressure and very high temperatures. Why would that be the case? Well, as we talked about before with the kinetic molecular theory, the temperature is a direct relationship of how fast the particles are moving. The faster they're moving, the less opportunity they have to actually stick to each other. The less we have to worry about them losing energy when they bounce into each other and bounce off the walls of the containers. All those things would actually be important for us in dealing with these ideal gases, okay, or making them seem as though they're ideal. This is why we spend so much time looking at what should we expect in an ideal situation, because then we can draw the parallel between the ideal and what happens in a non-ideal situation, everyday life situation. Now, the last thing that we're going to do is actually, that is the last thing we're going to do. We're going to go ahead and cut the video there. If you have questions or something's still not making sense, please do not hesitate to leave a comment down below or send me an email, and I will try to respond to your email as quickly as possible and see if that might be helpful for you. Have a good afternoon, and I look forward to seeing you at the end of the break.